Okay, because this is page 132 of the note spiral, and we're continuing with hypothesis tests for one sample t distributions. I'm going to do this one a little bit differently because I want to be able to speed through this. And when I say that, is that way because it's the third one, I assume that you've learned a lot, and I don't want to waste a whole lot of your time. So we're going to do this one a little bit faster, and so you may need to pause as you go through it. So a steel supplier claims that their bars have an elongation of 40% under a stress of 10 metric tons. All right, well that 40%, so this is the claim. 10 metric tons, a random sample of 12 steel bars, so we have a sample size of 12, was taken from a warehouse and the elongation measured in percent per every 2 inches. So we end up with this list of data. Is there evidence at an alpha level of 0.05 or at a level of significance of 0.05 to demonstrate that the elongation for the steel bars was different from 40? Well, the word different doesn't tell me less than, it doesn't tell me greater than. It means this is a not equal. All right, so this is going to be an alternative of not equal, which also means this will be a two-sided test. Less than is one-sided to the left, greater than one-sided to the right. Two tails means we have area or rejection zones on both sides, and then we will break into that in just a little bit. We start off by writing our null hypothesis. Our null is the status quo is that it's 40%. The alternative is that it's different than 40% or not equal to 40%. We need to make sure we define our parameter. And so let mu equal the true population mean for the percent of steel bar elongation. All right. Conditions, random sample. All right, a random sample was given. Thank you very much. We need to check to make sure that things are reasonably independent. So 12 divided by 0.10 is 120. And I'm just going to say that it's reasonable to assume that there are at least 120 bars. The next thing is our sample size is not 30 or larger. They didn't tell us it was normal. So I need to go ahead and enter in that into the calculator. So I go stat, edit, and I enter those values into the calculator. Once I enter them in the calculator, I go second, followed by the stat plot button. And just back up just a second. I'm going to clear out of that. Go to y equals. Make sure there's nothing in y equal. And hopefully you only have one stat plot on. So second quit. Then I'm going to go second, stat plot, enter, arrow to the left to make sure it's turned on, press enter, drop down, and select the box plot showing outliers. My data is an L1, so second one, and my frequency should be a number 1. If you keep getting a Y or something show up, hit alpha, the alpha button followed by the 1. So if you're getting something weird, press alpha followed by the 1, and that should take care of it. This needs to say 1. Once you have that, press zoom, followed by the 9, and you get a box plot that looks something like that. Remember, you can use the trace feature followed in combination with the arrows to get that. Well, when I look at that, it's not perfectly symmetric. It's not, but it's symmetric enough. So here's what we're going to say on that. The box plot is symmetric with no outliers. Always specify whether or not they're outliers. If there's an outliers, we have a problem. The distribution appears to be approximately normal, all right, or normal enough. And that's what my box plot actually looks like. The next thing we need to do is write the equation. And our equation is t equals x bar minus mu s divided by the square root of n. And I probably should take this moment to go ahead and draw what we're talking about. So we have a claimed mean of 40. And what we're looking for is an x bar that's too far to the left or an x bar that's too far to the right. All right, That's what we're looking for. All right. So anything that's in this area, we're going to reject, or anything in this area, reject. So we have two rejection zones because this is a two-tailed test. This area right here, we wanted to make this at an alpha level of 0.05. So this is 0.95. So our alpha is 0.05, and in this tail is 0.025, and in this tail is 0.025. Please remember, alpha is the area in the tails, and since we have two tails, we had to split it. Half is in this tail, half is in that tail. Now, at this point, I don't have an X bar. I don't have, so I don't have X bar and I don't have S. I can get those by going stat, calc, one variable statistics. My data is in L1. And now I end up with this X bar of 37.58 and a standard deviation of the sample. Make sure you're using the sample because we use sample values, is 3.175. So I'm going to plug into the equation. All right. And when I plug into the equation, it's going to look like that. Now you're going to notice something different. Normally I would go the probability that X bar is less than 37.58. Now you go, why didn't you use not equal? Well, because we came up with an X bar on this side. But this was supposed to be a not equal to. So anytime you have a two-tail, 2 times the probability, and if you're above, it'll be greater than, but since we're below, it's a less than, so 2 times the probability. This is for two-tailed. All right? And we'll explain why in just a moment. So this is what we're getting. Now, when I compare this to my critical values, I'm going to go second vars, inverse T. My area is going to be my area right here is 0.025 because it's 0.05 divided by 2. So 0.05 divided by 2. My degrees of freedom, 12 minus 1 is 11. And I end up getting a critical value of negative 2.2009, which means I also have a critical value of 2.2009. So if I get a probability greater than this, if I get a test statistic less than this or a test statistic more than this, I'm going to reject. So let's go ahead and run this test. Stat, test, t-test. And let's go ahead and use data because we know that we have our data in L1. Our mean or our hypothesis was 40. Second one. And we make sure the not equal is highlighted. And the calculator does the doubling for us. So we ended up with a test statistic of 2.636. Looking back at my chart right here, 2.636 is somewhere over here. So based on my test statistic, I would be rejecting. And I ended up getting a probability of 0.0231. Now notice the calculator did that for me automatically. Now we'll come back and look at this in just a minute. The calculator automatically did the doubling. I don't need to show it. All I need to do is make sure that I put a 2 out in front. Please make sure you put the 2 out in front. Other than putting the 2 out in front, it does the work behind the scenes. That's different, and remember, it's just because it's two-tailed. So our p-value is 0.0231, which is less than 0.05, and we're going to reject the null. That'll be our decision. Our p-value is 0.0231. We reject the null. There is sufficient evidence that alpha equal 0.05 to suggest that the true population mean for the percent of steel bar elongation, this is just rewriting the definition, is different because this is not equal to 40%. In other words, we didn't say whether it was greater than, we didn't say it was less than. Now we happen to know that it was less than that because of the test, but you always go with what the alternative statement was. You don't get to change it just because you learned something. So make sure that this has to be consistent with the alternative, must be consistent with the alternative. The alternative was not equal to, so we need to use the word different. All right. Now, I said I was going to do something on the doubling. So we have a t statistic of negative 2.636. So if I were drawing a picture of that, all t's are centered at 0. We have negative 2.636, and it's going to negative infinity. And we have degrees of freedom of 11. So I want to go back and check that out. So second vars, this time I'm going to use a TCDF because I want to find out the area right here. I'm looking for this area. And my lower bound is negative infinity, so I can just fill that up with a bunch of 9s. My upper bound is negative 2.636. And my degrees of freedom were 11. And I end up getting 0.0115. That's not what I got there. Why? Because the calculator automatically doubled it. So if I multiply that by 2, there we go, 0.0231. So we need to make sure that we always have this 2. Make sure we always have those 2 when we're working with a two-tailed, whenever we're working with a not equal, right? Only do it for two-tailed, but you need to make sure that you have it for two-tailed. All right, hopefully that helps. If you got questions, I will see you in tutoring. Thank you.